What's up, guys? It's Mr. Brengle, and today we're going to talk about our acceleration equation flowchart that we will use to help us pick the correct acceleration equation when doing our math problems. So, taking a look here at this flowchart, I have written down the different equations that you will typically use when doing some of these acceleration problems. And the first equation, there's really, both of these are the same equation here, but it's rewritten in different ways. It's solving for different variables, right? So this is solving for acceleration. It's the final velocity minus the initial velocity, otherwise known as change in velocity over time. Now, if we rearrange this for final velocity here, it would be acceleration multiplied by time plus initial velocity. I will come back and talk about what this is right here in a bit. The second equation that we have involves change in position. So we have the change in position of the object is equal to its initial velocity multiplied by time plus 1/2 times acceleration times t squared. I do want to clarify on this that essentially, in fact, I'm going to rewrite this. I'll end up erasing it. But delta x is equal to, this is together, vi times t, right? Plus, and then this is all together, but we need to be careful here. It's 1/2 a, and then the t is the only thing that is squared in this. I don't know why I put a bracket there, but the time is the only thing that's being squared here. So you could almost, if you wanted to, put another kind of parentheses around this. I just want to make sure we're very clear that the squared is only applying to the t in that equation. Now, if everything was in parentheses like this and the squared was around the outside of it, then that is squaring everything attached to it. So just to be clear about that. Now, the next one, the last one that we typically use here, also involves change in position, but there's no time in this one. So on this one, we have final velocity squared is equal to initial velocity squared plus, and then again, this is all multiplied together here, 2 times acceleration times change in position. Now, on each of these equations, you see some other things that I put down here that you can sub in. Basically, when we're dealing with a horizontal acceleration problem, meaning, for instance, like someone speeding up while in a car that's on a flat surface, they're moving left to right or right to left. That is the horizontal plane, in which case we will use delta x as our change in position. Think x-axis, horizontal. If it was a vertical change in position, like something falling or something being thrown up into the air, that is where you would want to use delta y. Think y-axis, x-axis, right? X-axis, y-axis. So if it's vertical, we want to use delta y instead of delta x. Similarly, if we have a horizontal acceleration, that's a number that we will either have to solve for or it's going to be given to us, and that would be the letter A here. But if something is in free fall, meaning that it's in the air and the only force acting on it is gravity, then it will accelerate at a rate that is caused by gravity, and we call that the acceleration due to gravity, and that is this little letter G here. And I've kind of put this on the other side of this. G is a known number, okay? We're going to use, it's technically 9.81 meters per second squared. It's a long decimal, but in this class, we will round up to 10 to make our calculations a little easier. So we use 10 meters per second squared. So really what that means is that when an object is, say, falling, like if I drop this pen, it will start at 0 meters per second, and it's going to increase its speed by 10 meters per second each second that it's in the air. So after 1 second of falling, it would be at 10 meters per second. And then during that next second, it will gain another 10 meters per second of velocity. So it would be at 20 meters per second by the time 2 seconds have passed, and so on and so forth. Okay, so that is something that when you are given a vertical problem where something is falling or is being thrown up into the air, you will go ahead and put g in, and you already know that number, so it often won't even tell you. It's an assumption that you have to make. So anyway, that is the difference in the equations there, and we just need to make sure that we clarify if the question is horizontal acceleration or vertical acceleration is the object in free fall. Those things will be helpful. So now, how do we choose between these equations? It can be hard because they all have similar variables. They all have acceleration in them, right? They all have the letter A. There's different velocities, initial, final. We've got initial velocity here. We've got initial and final over here. There's change in position here, change in position here. There's time, there's time. So it can get pretty jumbled up and hard to pick an equation. This is why I have you guys write your variables out on your known variables and your unknown on the side so that we can then pick an equation. So once you have done that for a given problem, you need to ask yourself 2 questions to get to the right equation. And there are other ways to do this, but this way is very, very simple. So I'll help walk you through that. So the first one is, once we have our variables, does the problem give us a number for, or ask us to solve for change in position, which would be delta x or delta y. The reason we're asking this question is because 2 of the 3 equations have a change in position variable in them. So equation 1 does not have delta x or delta y in the equation. There's no change in position that's needed to use this equation. However, we have change in position here and here in equation 2 or 3. So if our first question is to look for delta x or delta y, depending on if it's vertical or horizontal, if the answer to this is no, that we were not given a number for it and we don't need to solve for it, then it's super easy. You've already found the equation that you want to use. It is number 1, because number 1 does not have the change in position variable in the equation. So we would just use this. Now, if you answered yes, that it did give me a number for that, or yes, I need to solve for it, then we just move on to the next question, right? And the next question here is going to ask us the same thing except time. Did the problem give us a number for time or ask us to solve for time? And again, the reason for that is the variable that is different between equations 2 and 3. Equation 2 has time in it. Equation 3 does not. They both have change in position, right? So if you answer yes, we do need the time, or yes, we were given the time, then you are going to go with equation number 2, because number 2 has change in position and it has time. Okay? And then, of course, if you answer no, that we don't have the time and we don't need to find the time, then we will go ahead and choose equation 3. Okay, but before I do that, I better put this over here so we don't forget. There's time. And then, of course, equation 3 would go right here. Vf squared is equal to Vi squared plus 2a delta x. And remember, you can always sub in delta y for delta x, and you can always sub in g for a. So this is kind of, in a nutshell, the process for how to pick the correct equation when looking at these acceleration equations. It can be a little overwhelming. The best way to learn is just to practice it. So we'll want to apply this to some of our practice problems, but you want to take a look at this first so you know kind of how to attack it when you do get your problems. And then you might consider also writing these things down on the back of the paper if you didn't already do that. This will just kind of help you identify what you're looking at, and that'll be good. So if you need to pause the video to do that, please feel free to do so. All right, well, thanks for sticking with me, and I hope you learned something.